The night of September 7th, 1940, Flight Lieutenant Harold Balfour sat in the cramped cockpit of his Avro Anson, circling at 8,000 feet over Kent. His hands gripped a device that looked like it belonged in a physics laboratory, not a military aircraft. 2 crude oscilloscope dials, a tangle of wires, and a receiver cobbled together from salvaged radio parts. He was hunting something the Germans believed was invisible, a radio beam. And on this night, he would prove that the Luftwaffe's most sophisticated navigational technology, the system that was supposed to guarantee the destruction of London, could be turned against them with nothing more than clever physics and audacious deception. This was the secret electronic war within the war. While Spitfires and Hurricanes fought in daylight skies, a different battle raged in the electromagnetic spectrum. The Germans had developed Knickebein, a revolutionary radio beam system that allowed their bombers to navigate with precision through the darkest nights, through clouds, through conditions that made visual navigation impossible. They believed this technology was undetectable, unjammable, and would deliver German bombs onto British cities with mathematical certainty. They were catastrophically wrong. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story begins not with pilots or bombers, but with a prisoner of war and a chance conversation that would change the course of the Blitz. In May of 1940, just weeks after the fall of France, a captured German bomber pilot named Oberleutnant Hermann Schmidt sat in an interrogation room at the Combined Services Detailed Interrogation Centre outside London. He was cocky, certain that Germany's technological superiority guaranteed victory. The British interrogator, Squadron Leader Reginald Jones, was only 28 years old, a scientific intelligence officer who had been pulled from his physics research to join the intelligence service. He had been asking routine questions about German bombing accuracy when Schmidt made an offhand comment that would unlock everything. "Your blackout will mean nothing," Schmidt said, lighting a cigarette with the confidence of a man who believed the war was already won. "We do not need to see your cities to destroy them. We have methods you cannot imagine." Jones pressed carefully. "Methods?" "Knickebein," Schmidt said, then caught himself, realizing he had said too much. But it was too late. That single word, crooked leg in German, would lead British scientists to discover one of the Luftwaffe's most closely guarded secrets. Jones immediately began investigating. The name meant nothing initially. No intelligence reports mentioned it. No captured documents referenced it. It was as if the word didn't exist. But Jones had learned that the most valuable secrets are the ones that leave no paper trail. He began examining transcripts of intercepted German radio communications, looking for any mention of the mysterious term. On June 5, 1940, a signal intelligence unit at RAF Cheadle intercepted a transmission from a German bomber testing its equipment before a raid. The message was routine, procedural, but it contained a phrase that made Jones's pulse quicken. "Beacon key Knickebein functioning correctly. Signal strength adequate for precision navigation." It wasn't a weapon, it was a navigation system. And if the Germans were testing it over Britain, that meant the beams were already operational. Jones brought his findings to Frederick Lindemann, Winston Churchill's chief scientific advisor. Lindemann was skeptical. Radio beams accurate enough for blind bombing seemed technologically implausible given the wavelengths and equipment available in 1940. But Jones was persistent. He argued that if the Germans had solved the technical challenges, if they had deployed this system without British knowledge, then every night raid would become a precision strike. London, Coventry, Birmingham, every major city could be bombed with accuracy regardless of weather, darkness, or British defences. Churchill, always attentive to technological threats, ordered an immediate investigation. On June 12, 1940, he summoned Jones to a meeting at number 10 Downing Street. The young scientist found himself in a room with the Prime Minister, the Air Staff, and Britain's top radar experts. The scepticism was palpable. "You're telling us," Air Marshal Hugh Dowding said, his voice carrying the weight of a man who commanded fighter command, "that the Germans can guide their bombers using radio waves we cannot detect." "Not cannot detect, sir," Jones replied, his voice steady despite the scrutiny. "Have not been looking for. The wavelength would be different from our radar systems. Longer waves, lower frequency. We've been focused on our own chain-home radar. We haven't been listening for German navigational transmissions." Churchill leaned forward, his eyes sharp. "Can you find these beams, Doctor? Jones?" "If they exist, Prime Minister, I believe we can." "Then find them. You have 72 hours. What followed was one of the most intense scientific investigations of the war. Jones coordinated with RAF listening posts across southern England, ordering them to scan frequencies between 30 and 60 megahertz, a range they had previously ignored. For 2 days, they found nothing. Jones began to doubt himself. Perhaps Schmidt had been boasting. Perhaps the technology was still experimental. Then, on June 14, 1940, at precisely 9:45 in the evening, a listening post near Dover detected something extraordinary. A steady, modulated radio signal at 31.5 megahertz, far stronger than any normal radio transmission. The signal formed a narrow beam, perhaps 400 meters wide, extending from the German coast directly over London. Jones was contacted immediately. The oscilloscope trace was unmistakable. 2 overlapping signals, one continuous, one in Morse dashes. When an aircraft flew along the center line where the signals overlapped, a pilot would hear a steady tone, drift to either side, and the tone would break into dots or dashes, telling the pilot to correct course. It was brilliant, it was simple, and it was already operational. The technical elegance was undeniable. The Germans had taken a commercial blind landing system, scaled it up, and weaponized it. The Lorenz system, used at civilian airports across Europe before the war, allowed aircraft to land in fog by following radio beams to the runway. The Luftwaffe had simply extended the range from 20 kilometers to 400, mounting powerful transmitters on the occupied French coast. But the true genius, from the German perspective, was the beam's narrowness. Unlike a broadcast radio that spreads in all directions, these were directed beams, focused like searchlights. The Germans believed they were undetectable unless you flew directly through them. They believed the British lacked the equipment and expertise to even search for them. They were wrong on both counts. Jones presented his findings to Churchill on June 16th. The implications were staggering. The entire Luftwaffe bomber fleet, some 1,800 aircraft, could now navigate to any target in Britain with accuracy measured in hundreds of meters, not miles. Night bombing, previously an exercise in scattering explosives randomly across the landscape, had become a precision weapon. "How accurate?" Churchill asked. "In perfect conditions," Jones explained. "A bomber following the beam could place its bombs within 250 meters of the aiming point. That's close enough to hit a factory, a rail yard, or a government building." Churchill was silent for a long moment. Then he asked the crucial question. "Can we stop them?" "Yes, Prime Minister, but not by destroying the transmitters. They're in occupied France, beyond our reach. We'll need to fight them in the electromagnetic spectrum. We need to jam the beams, bend them, make them unreliable. We need to turn their precision guidance system into a liability." Churchill's response was immediate. "Do it. Whatever resources you need, personnel, equipment, authority, consider this a priority equal to fighter command." And so, in the summer of 1940, while the Battle of Britain raged in daylight skies, a parallel war began in the invisible realm of radio waves. A war that would save thousands of British lives and expose the fatal flaw in German technological arrogance. The British countermeasure programme, codenamed Operation Headache, began with a desperate shortage of everything. The entire British electronic warfare capability in June of 1940 consisted of Jones, a handful of engineers, and equipment scavenged from university laboratories and radio stations. The man chosen to lead the operational effort was Wing Commander Edward Addison, a former radio engineer who had joined the RAF in 1936. Addison understood that they faced 3 immediate challenges. First, they needed to map all the German beams crossing Britain. Second, they needed to design jamming equipment powerful enough to interfere with the German signals. Third, they needed to do all of this before the Luftwaffe began their nighttime campaign in earnest. They had perhaps 6 weeks. Addison assembled a team of radio operators, engineers, and pilots. They flew systematic search patterns across southern England in elderly Avro Ansons, cramped twin-engine aircraft never designed for electronic warfare. The planes were fitted with crude receivers built from commercial radio components. The operators sat hunched over oscilloscopes, watching for the telltale pattern of Knickebein signals. By mid-July, they had mapped 3 separate beam systems converging on London, with additional beams aimed at Birmingham, Coventry, and Liverpool. Each transmitter station in France could generate multiple beams, retargeted nightly based on Luftwaffe operational plans. The Germans had created an invisible spiderweb across Britain, guiding their bombers to targets with cold precision. The mapping flights were dangerous work. The Ansons flew slowly, methodically, often at night when German beams were active. They were unarmed, vulnerable to both German fighters and British anti-aircraft guns that couldn't distinguish friend from foe in the darkness. Flight Lieutenant Balfour, who had volunteered for the first reconnaissance missions, described it as flying through a battlefield with your eyes closed, searching for ghosts. But the most dangerous work was still ahead. Finding the beams was only the first step. Disrupting them required a completely different approach. The technical challenge was formidable. The German Knickebein transmitters were powerful, broadcasting at 50 kilowatts, equivalent to a major commercial radio station. British jammers would need to overpower these signals without alerting the Germans that their beam system had been compromised. If the Luftwaffe realized the British were jamming, they would simply change frequencies or modify their system. The solution came from Robert Cockburn, a 26-year-old engineer at the Telecommunications Research Establishment. Cockburn proposed a method called meaconing, after the old nautical term for false lights that lured ships onto rocks. Instead of crudely jamming the German beams, British transmitters would broadcast false signals on the same frequency, slightly offset from the true beam. A German pilot following what he believed was the Knickebein beam would actually be following a subtle blend of the real signal and the British counterfeit. The effect would be gradual, almost imperceptible. The bomber's course would drift just a few degrees, not enough to trigger immediate alarm, but enough to place the aircraft miles from its intended target by the time the bombardier pressed the release switch. The genius of meaconing was its subtlety. German pilots wouldn't realize they had been deceived until their bombs exploded in empty fields instead of crowded cities. And even then, they might attribute the error to equipment malfunction or pilot error rather than British interference. But building the meaconing system required equipment Britain didn't have, and time they couldn't spare. Cockburn needed high-powered transmitters, precise frequency control, and operators who could track German beams in real time and match their modulation perfectly. He needed all of this installed and operational before the Blitz began. He had 3 weeks. The crash program to build Britain's meaconing network was a masterpiece of improvisation. Transmitters were commandeered from BBC radio stations. Antennas were erected in fields across southern England, often just miles behind the frontline coastal defences. The sites were staffed by hastily trained operators, many of them women from the Women's Auxiliary Air Force, who learned to read oscilloscopes and adjust transmitter settings with precision that would determine whether bombs fell on cities or countryside. The first meaconing station became operational on August 15, 1940, at a site near Winchester. The timing was fortunate. That very night, a force of 60 Heinkel He-111 bombers took off from bases in occupied France, their mission to destroy aircraft factories in Birmingham. Each bomber was guided by Knickebein, following the radio beam with confidence born from dozens of successful training missions. What the German pilots didn't know was that as they crossed the English coast, British operators at Winchester began transmitting their false beam. The meaconing signal was carefully calibrated, just slightly offset from the true Knickebein bearing. The German pilots, trusting their instruments, made minute corrections to stay on what they believed was the precise beam centerline. The navigators never noticed they were drifting south of their intended track. Their instruments showed perfect alignment. Their training had taught them to trust the technology absolutely. When they reached what their navigation equipment indicated was Birmingham, they released their bombs on schedule, on heading, by the book. The 200 tons of high explosive and incendiary bombs fell on empty countryside 15 miles south of Birmingham. Farms were cratered, sheep were killed, but not a single factory was hit, not a single war worker injured. The entire raid, planned with German precision and executed with German efficiency, had been rendered completely ineffective by British electronic deception. The German after-action reports from that night make fascinating reading. Pilots described perfect navigation, clear beam signals, and textbook execution. Yet somehow, the bombs had missed. The explanations offered were revealing: equipment malfunction, unexpected winds, map errors, pilot fatigue. Never did they consider that the beam itself had been compromised, that British scientists had penetrated their most sophisticated secret and turned it into a weapon against them. This would become the pattern for the next 6 months. German bombers, guided by what they believed were infallible electronic systems, would drop their deadly cargoes on fields, forests, and empty villages while British cities endured reduced, though still terrible, destruction. But the story of how British electronic warfare defeated Knickebein is also a story of the men and women who operated the meakening stations, working invisible shifts in isolated facilities, knowing that their precision meant the difference between life and death for thousands of people they would never meet. The meakening stations were austere places. Most were Nissen huts, those corrugated metal half-cylinders that became the ubiquitous architecture of wartime Britain, placed in farmers' fields or on windswept hillsides. Inside, the temperature swung from freezing in winter to stifling in summer. The equipment generated tremendous heat, the transmitters glowing with thermionic valves that needed constant monitoring. Section Officer Dorothy Harper, a 23-year-old WAAF operator, worked the night shift at the Winchester station from August 1940 through May 1941. Her memoir, published in 1987, provides a rare glimpse into the daily reality of electronic warfare. "We knew lives depended on our precision," she wrote, "but we never saw the results of our work. We sat in that hut, watching oscilloscope screens that showed nothing but wavy green lines, adjusting dials with movements measured in millimeters. The German beam would appear on our display, and we would match it, creating our false signal just slightly offset. Too much offset, and the German pilots would notice. Too little, and the effect would be negligible. We aimed for 3 degrees of deflection. That was the sweet spot where their instruments would read normally, but their position would drift miles off course." Harper described the psychological toll of the work. "You never knew if you'd succeeded. We'd work a 6-hour shift, concentrating absolutely on maintaining perfect signal characteristics, and then go to our bunks not knowing if we'd saved lives or if our equipment had failed and bombs had fallen on sleeping families. The not knowing was the hardest part." But unknown to Harper and her colleagues, their work was being meticulously documented. RAF reconnaissance flights the morning after major raids would photograph the crater patterns, mapping where German bombs actually fell versus where they were aimed. The intelligence analysts who compiled these reports saw patterns that astounded them. A typical raid intended for the Bristol aircraft factories at Filton would see bombs scattered across a 15-mile arc south of the target. A raid aimed at the Liverpool docks would crater fields in North Wales. The Luftwaffe's vaunted precision navigation system was producing consistent errors that saved not just individual buildings, but entire neighbourhoods. Wing Commander Addison's weekly reports to the Air Ministry tracked the success rate with stark statistics. In August 1940, before meakening was fully operational, German night raids achieved an average targeting accuracy of 800 meters from the aiming point. By September, with 5 meakening stations operating, that accuracy had degraded to 4,000 meters. By October, with the system refined and expanded, the average error had grown to 7 miles. 7 miles. In urban warfare, That's the difference between destroying a munitions factory and bombing a residential suburb. That's the difference between crippling Britain's war production and killing sheep. But the German reaction to these failures revealed the same institutional blindness that would later plague their Enigma security. Luftwaffe intelligence officers, analyzing the pattern of bombing errors, generated increasingly elaborate explanations that never questioned the integrity of Knickebein itself. Their first theory blamed British weather. The meteorological conditions over Britain, they reasoned, must be creating atmospheric distortion of the radio beams. This explanation seemed plausible, until raids conducted in perfect clear weather showed identical errors. The second theory involved magnetic anomalies. Perhaps Britain's geography created localized magnetic fields that interfered with compass readings, causing pilots to drift off the beam without realizing it. This theory persisted for several weeks until someone pointed out that the beam guidance system didn't use magnetic compasses. The third explanation was the most damning to German aircrew morale. Perhaps, Luftwaffe command suggested, the pilots themselves were at fault. Navigation errors, fatigue, incompetence. This accusation infuriated experienced bomber crews, who knew they had followed procedures perfectly. The psychological impact was significant. Crews began to doubt themselves, creating tension between aircrews and command staff. Never once did German investigators seriously consider that the British had penetrated Knickebein and were actively manipulating it. The system's mathematical elegance, its theoretical invulnerability, had become a mental barrier preventing them from seeing the obvious truth. But by late October 1940, German intelligence finally began to suspect something more sinister was happening. The evidence was becoming too consistent to ignore. Every major raid was missing its target by similar margins. The pattern was too regular to be random chance or pilot error. On October 28th, Luftwaffe Signals Intelligence issued a report that sent shockwaves through German command. Enemy activity on Knickebein frequencies has been detected. Possibility of intentional interference cannot be excluded. Recommend immediate investigation and countermeasures. The Germans responded with characteristic thoroughness. They conducted electronic reconnaissance flights over Britain, mapping British radio transmissions. They modified Knickebein frequencies, trying to find wavelengths the British weren't monitoring. They introduced sudden frequency changes mid-flight, hoping to break the British jamming lock. Nothing worked. The British beaconing operators, now numbering over 300 trained personnel at 12 stations across Britain, adapted to every German modification within hours. When frequencies changed, British operators found the new beams and resumed jamming. When beam characteristics were altered, British equipment matched the changes. The electronic chess match had entered a new phase. Both sides were now aware of each other, but the British held one critical advantage. They were on the defensive, reacting to German moves on their own territory with short response times. The Germans were projecting power across the channel, unable to verify whether their beams were functioning correctly, until their bombers returned with reports of missed targets. In November 1940, the Germans deployed their response. X-Gerät, a far more sophisticated beam system that used multiple intersecting beams and timing mechanisms. Where Knickebein was elegant in its simplicity, X-Gerät was complex to the point of genius. The system worked by having the bomber fly along one main beam while crossing several perpendicular beams at precise intervals. By measuring the time between beam crossings, the bombardier could calculate ground speed and determine the exact moment to release bombs, compensating for wind drift and aircraft velocity. It was, on paper, unjammable. The British couldn't fake the timing of beam intersections. They couldn't create false perpendicular beams without knowing their precise locations and timing sequences. Reginald Jones, when he learned of X-Gerät from intercepted Luftwaffe communications, immediately recognized the threat. This wasn't just an evolution of Knickebein. It was a completely different approach that might render beaconing ineffective. The first X-Gerät raid targeted Coventry on November 14, 1940. The Luftwaffe assembled 437 bombers, the largest night raid yet attempted. The target was the city's industrial heart, home to aircraft engine factories, machine tool works, and precision manufacturing plants critical to Britain's war effort. British intelligence, reading German communications through Ultra, knew the raid was coming. They knew Coventry was the target. What they didn't know was whether their electronic countermeasures would work against X-Gerät. The raid was a partial German success and a harbinger of the electronic battle's future. The Pathfinder Force, elite crews using X-Gerät, marked Coventry accurately with incendiary bombs. The main bomber stream, still using the older Knickebein system, followed the fires and added their high explosives. The result was devastation. 568 people killed, the medieval cathedral destroyed, and significant damage to war production. But post-raid analysis revealed something crucial. The X-Gerät Pathfinders had placed their markers accurately. However, the British had successfully jammed the Knickebein beams, guiding the main force. Without the meaconing, the entire bomber stream of over 400 aircraft would have followed X-Gerät markers onto the target with precision. Instead, approximately 30% of the bombs fell outside the city, deceived by jammed beams. It wasn't enough. Coventry burned, but it was proof that even against improved German technology, British electronic warfare could reduce casualties. The question was whether they could do better. Dr. Robert Cockburn returned to his laboratory at the Telecommunications Research Establishment with new urgency. X-Gerät had to be defeated, but the timing mechanism seemed insurmountable. You couldn't fake precise time intervals between beam crossings. Unless, Cockburn realized, you changed the bomber's perception of time itself. The solution he developed was called masking. British transmitters would broadcast noise on X-Gerät frequencies at the exact moment a German bomber crossed a timing beam. The noise would be brief, less than 2 seconds, but during that critical window, the German bombardier's stopwatch would keep running while his receiver was effectively blind. The timing discrepancy would be small, perhaps only 1 or 2 seconds, but at bomber speeds of 200 miles per hour, 2 seconds equals nearly 600 feet of horizontal distance. Multiply that error across 3 timing beams, and bombs would fall hundreds of meters from the intended point. It was a temporary solution, buying time while British scientists developed more sophisticated countermeasures, but it worked. Raids using X-Gerät throughout December 1940 and January 1941 showed increasing inaccuracy as British masking techniques improved. The Germans responded by introducing WWII, the third and most sophisticated beam system. This used a single beam with a transponder system that measured distance by radio reflection. It was simpler than X-Gerät, harder to jam, and theoretically more accurate. But by this point, the pattern had been established. The Germans would innovate, deploy their innovation with confidence in its invulnerability, and the British would penetrate and defeat it within weeks. The cycle repeated through the spring of 1941, each German advance met by British countermeasures. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. What made the British success remarkable wasn't just technical innovation, but organizational flexibility. The German military, for all its operational excellence, was bureaucratic in its approach to technology. New systems went through lengthy development, testing, and deployment cycles. Changes to deployed systems required approval from higher authority. The British electronic warfare effort, by contrast, operated with remarkable autonomy. Cockburn and his team could design, build, test, and deploy new countermeasures in days rather than months. Operators in the field had authority to modify procedures based on real-time observations. The system was designed to learn and adapt faster than the German decision cycle. Corporal James Mitchell, an operator at the Beacon Hill Meekening Station, exemplified this flexibility. On the night of February 8, 1941, during a raid on Portsmouth, Mitchell noticed something unusual in the German beam characteristics. The modulation pattern was changing every few minutes, cycling through different frequencies in what appeared to be a deliberate attempt to break the jamming lock. Rather than waiting for instructions from headquarters, Mitchell adapted on the spot. He began manually tracking the frequency changes, adjusting his transmitter to follow the German beam through its variations. His quick thinking maintained the meaconing effect throughout the raid, preventing the Germans from achieving the accuracy they sought. Mitchell's initiative was rewarded not with a medal, his work was too secret for public recognition, but with promotion to sergeant and a role training other operators in adaptive jamming techniques. His method was codified into standard procedures within 72 hours. This organizational agility, the ability to observe, adapt, and disseminate improvements across the entire network in days, gave Britain a decisive advantage in the electronic war. The Germans were fighting with precision and planning. The British were fighting with precision and improvisation. By spring of 1941, the Luftwaffe was facing a crisis in night bombing accuracy. Morale among bomber crews was deteriorating. Pilots, who had been assured their navigation systems were infallible, were consistently missing targets. The psychological impact was corrosive. Generaloberst Hans Jeschonek, chief of the Luftwaffe General Staff, convened an emergency conference in March 1941 to address what was now openly called the accuracy problem. The meeting brought together signals intelligence officers, operational planners, and technical experts. The conclusions reached at that conference are preserved in captured German documents now held at the National Archives. They reveal a leadership struggling to comprehend systematic failure. The final report acknowledged British interference with German beam systems but concluded, incredibly, that the interference was not technically significant and attributed continued bombing errors primarily to operational factors and crew performance. This institutional blindness would persist throughout the Blitz. Even when German engineers correctly identified British meaconing and proposed effective countermeasures, implementation was slow and incomplete. The bureaucracy that had created such sophisticated systems couldn't adapt quickly enough when those systems were compromised. The human cost of British electronic warfare success is difficult to quantify precisely, but post-war analysis provides estimates. Professor R.V. Jones, in his memoir Most Secret War, published in 1978, calculated that meaconing and related countermeasures caused German bombers to misplace approximately 40 to 50% of their bomb loads during the Blitz. The London Blitz alone, from September 1940 through May 1941, saw 57 consecutive nights of bombing followed by sporadic raids. Total German bombs dropped, 18,000 tons of high explosive and 17,000 tons of incendiaries. British estimates suggest that without electronic warfare countermeasures, bomb distribution would have been concentrated on strategic targets with devastating effect on war production and morale. Instead, significant percentages fell on suburbs, countryside, and non-strategic areas. This doesn't diminish the horror experienced by those who did suffer. Over 40,000 British civilians died during the Blitz, but it means that the death toll could have been catastrophically higher without the invisible shield provided by electronic warfare. The campaign of the Beam War reached its climax in May 1941 with the last major raid on London. On the night of May 10th, 505 German bombers attacked the capital, dropping 700 tons of high explosive. The raid killed 1,436 people, the highest death toll of any single night during the Blitz. But intelligence analysis of that raid revealed something remarkable. The intended target was the London docks and the industrial complexes along the Thames. However, British meaconing had been particularly effective that night. Approximately 60% of German bombs fell outside the primary target zone, many in residential areas that, while still causing terrible casualties, represented a failure of German strategic bombing doctrine. Had those bombs fallen on their intended targets, the Port of London, already strained by months of bombing, might have been rendered unusable. Britain's ability to receive supplies from America would have been severely compromised. The war's outcome might have hung on that difference. Then, suddenly, the Blitz ended, not because of British defences or electronic warfare, but because Hitler turned east. Operation Barbarossa, the invasion of the Soviet Union, required the transfer of Luftwaffe units from the west. The strategic bombing of Britain became a secondary priority. The Beam War didn't end, but its character changed. German night raids continued sporadically through 1942 and 43, but never with the intensity or scale of the Blitz. British electronic warfare units, their skills honed and their equipment refined, achieved increasing effectiveness against each raid. By 1943, German night bombing of Britain had become almost random in its inaccuracy. A raid intended for Sheffield might scatter bombs across Yorkshire. An attack aimed at Birmingham might hit Staffordshire. The combination of British jamming, meaconing, and by then, effective night fighter defences made German night bombing operations more dangerous than productive. The institutional knowledge gained from defeating the German beams would pay dividends when the strategic situation reversed. As Bomber Command began its own night offensive against Germany, British navigators used more sophisticated versions of the same beam technology the Germans had pioneered, but they incorporated lessons learned from defeating Knickebein, making their systems more resistant to jamming and deception. The technical expertise developed in those cramped Nissen huts across southern England by young WAAF operators watching oscilloscope traces and adjusting transmitter dials became the foundation for the entire field of electronic warfare. After the war, those techniques evolved into radar jamming, missile guidance systems, and eventually the electronic warfare capabilities that define modern military operations. But for the men and women who fought the Beam War, recognition came slowly, if at all. The work remained classified for decades. Dorothy Harper, the WAAF operator from Winchester, couldn't tell her own children what she'd done during the war until the late 1970s, when the Official Secrets Act restrictions were finally lifted. "When I could finally explain," she wrote, "my daughter asked if I'd received any medals. I told her no, we'd received something better. We'd received tomorrow. Every person who survived the Blitz because German bombs fell in empty fields instead of on their homes, they were our medal. We just never knew their names." The Beam War's legacy extends beyond the immediate tactical victories. It represented a fundamental shift in military thinking. For the first time, warfare was fought not just with visible weapons, but in the electromagnetic spectrum. The side that could dominate that invisible battlefield gained advantages that translated directly into lives saved and strategic objectives achieved. Reginald Jones, who orchestrated much of Britain's electronic warfare strategy, received proper recognition after the war. He was knighted, returned to academia, and wrote extensively about the scientific intelligence work that had been crucial to victory. In his lectures at the University of Aberdeen, where he became Professor of Natural Philosophy, he would tell students that the Beam War taught a crucial lesson about the relationship between technology and warfare. The Germans had superior technology, he would say. Their beam systems were more sophisticated than anything we had developed, but they made a fatal error. They assumed technological superiority guaranteed operational success. They never imagined that clever application of simpler technology, combined with organizational flexibility, could defeat their elegant systems. That assumption, that certainty in the face of contrary evidence, cost them the Battle of Britain as surely as if they'd lost it in the daytime skies. Flight Lieutenant Harold Balfour, who flew those early reconnaissance missions hunting for invisible beams, survived the war and lived until 1996. In an interview conducted for the Imperial War Museum in 1994, he reflected on the strange nature of the war he'd fought. "We never saw the enemy," he said. "Not directly. We saw oscilloscope traces and heard radio tones. We fought the war looking at instruments, adjusting equipment, making calculations, but the enemy was there, as real as any fighter pilot I'd fought, and when we won, when we successfully jammed or bent their beams, we saved lives we'd never see, protected people we'd never meet. It was the strangest feeling, fighting a battle where victory was invisible and defeat was measured in deaths that didn't happen." The final vindication of Britain's electronic warfare effort came from an unexpected source. After the war, Allied interrogators questioned Luftwaffe officers about the beam systems. General Major Wolfgang Martini, who had overseen much of the Luftwaffe's signals intelligence, was asked directly why the Germans had persisted with beam navigation when British countermeasures were so effective. His answer revealed the core of German institutional blindness. "We knew the British were interfering with our beams," he said, "but we never imagined they could do it so effectively. Our mathematical models showed that with our transmitter power and beam characteristics, successful jamming would require British resources we thought impossible to mobilize. We assumed they were making crude attempts that occasionally succeeded through luck. We never realized they had turned our technology against us so systematically." When shown post-war analysis of British meekening effectiveness, how consistently raids had been diverted from their targets, Martini sat in silence for several minutes. Finally, he said, "Then we were fighting a war we couldn't win. Every night our bombers took off. They were already defeated before they crossed the Channel. The tragedy is that our own confidence prevented us from seeing it." The Beam War officially ended in May 1945, with Germany's surrender. The meekening stations were decommissioned, their equipment salvaged for other purposes. The transmitter sites returned to farmland. The Nissen huts where Britain's invisible war had been fought were torn down or converted to agricultural use. Today, few physical traces remain of the electronic battleground that stretched across southern England. A small memorial plaque at the site of the Winchester station honours the WAAF personnel who served there, though the specific nature of their work isn't detailed. The National Archives holds the operational records, declassified over decades, telling the story of one of World War II's most crucial yet least understood campaigns. The men and women who fought the Beam War mostly returned to ordinary lives. Some continued in electronic warfare during the Cold War, their expertise too valuable to lose. Others returned to civilian careers, carrying secrets they couldn't share for 30 years. They had prevented catastrophe through the invisible application of physics and courage, and their reward was the knowledge that they'd saved lives, even if they never knew exactly whose lives or how many. The story of how RAF electronic warfare defeated Luftwaffe navigation beams is ultimately a story about the limits of technological certainty. The Germans created sophisticated systems and assumed those systems were invulnerable. They couldn't imagine that the British would develop effective countermeasures so quickly or implement them so comprehensively. That failure of imagination, that certainty in the face of mounting evidence to the contrary, cost them the ability to conduct effective strategic bombing against Britain. It didn't win the war for Britain, but it prevented Britain from losing it during those desperate months when survival hung by threads. And it was accomplished not by superior technology, but by superior adaptation. By people like Dorothy Harper watching oscilloscope screens through long nights. By engineers like Robert Cockburn designing countermeasures in days that should have taken months. By operators like Corporal James Mitchell adapting procedures in real time during actual raids. By scientists like Reginald Jones who saw possibilities where others saw impossibilities. They fought a war most people never knew was happening, against an enemy that never appeared on radar or in gun sights. They fought with mathematics and electronics, with transmitters and receivers, with patience and precision. And they won. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.